In this video, we describe a series of experiments that characterize the atom or help characterize the atom. Right, so with the fundamental chemical laws and Dalton's atomic theory, the idea of an atom was at play, and that's how people explained the structure of substances and matter. Okay, but still, there were a lot of unknowns about what an atom really was and why atoms of different elements were different. Right, so this is now 100 years later, 100 years after Dalton's atomic theory, and people were able to do experiments to actually characterize what is an atom. Right, so the first set of experiments that we're going to talk about here were the experiments by Thompson with a cathode-ray tube. Okay, so the experiment is as follows. Imagine here a glass vial, a large glass vial, that has two electrodes. One that is going to be negative, okay, so that is the cathode, and one that is going to be positive. Now, you can have here a source of potential, okay, and apply a huge electrical discharge to these electrodes and see what happens. That's the story. Now, this glass vial is evacuated, so there's a very little gas inside. Now, the observation is that when you have this electrical discharge, there's actually a ray of particles that emanate from the cathode and end up in the anode. Okay, so that's a ray that you can actually visualize if you get clever about visualizing those electrons, okay, or that beam. And actually, this needs to have a negative charge, okay, because it goes from the negative electrode to the positive electrode. Okay, so those particles that are forming part of the beam receive the name of electrons. Okay. Now, the key of Thompson experiment is to recognize that this beam of electrons, of negatively charged particles, happens regardless of what metal you put in electrons. Okay, so it seems that the electrons are not particular to any atom. They actually are general to all of the atoms. Okay, so it looks like an electron could be a subatomic particle, right? Something that is forming part of an atom. Okay, so that's a discovery of the electron, a particle that is negatively charged and that is a constituent of an atom. Now, something interesting that Thompson also did is you can actually apply here an electric field. Okay, so put here two plates, positively and negative, and what that means is that you're going to observe here some deflections of this negatively charged beam of particles. Right, so with those deflection experiments, measuring the angles according to the field that you're applying, you can actually come up with a mass to charge ratio. Okay, so this number, the mass of electron divided over its charge, was known from Thompson experiment. Now, they didn't know exactly how much the mass was or the charge. It was negative, but nothing known about the size of the charge, but they knew the ratio of those two. Okay, so that is really interesting. Okay, now so from these experiments, a model came up, which is called the Plum pudding model. In that, well, an atom, you can imagine that is going to be, this is a cross section of an atom. Okay, and because these electrons can be generated from the atom, all those electrons are going to be somewhere in this atom. Okay, distributed likely randomly. Okay, but we also know that matter is electrically neutral. Okay, so if you have negative particles, then there has to be a positive charge so that overall you don't have any charge at all. Now, where the positive charge is in this Plum pudding model, okay, should be somewhere around here in a diffuse way. Okay, so that overall you have exactly the same size of positive charge as you do of negative charge. Okay. Now, of course, this is a cross-section of what an atom should be. In reality, this is an atom should be a three-dimensional object, likely spherical. Okay, so that's where the Plum pudding model comes from. Now, the next experiment after this model emerged was by Millikan, and Millikan got very clever and was able to actually measure the charge of the electron, which is a very small quantity. And of course, if you have the charge and the mass-to-charge ratio, from Millikan's experiment, you could actually determine what the mass of the electron was. And this mass is actually shockingly small. Okay, so the mass of an electron is 9.11 10 to the minus 31 kilograms. Okay? By reference, the mass of a typical human is about 65 kilograms. the mass of this marker is about 0.01 kilogram or so. Right, so of course this, what this tells you is that electrons are ridiculously small. Okay, they're very, very tiny, and we'll actually talk about the size of the atom a little bit later on. Okay, but that's something that was already known. This was at the turn of the 20th century. Okay, so we know that the atom contains negatively charged electrons, and then the mass of those electrons is very, very small. Okay, so what is the next experiment that helped characterize the atom? The next experiment was done by Rutherford, and by shining something that is called alpha particles through a thin foil of a metal. Okay, so now we erase these old experiments, and then think about the Rutherford experiment. Okay, so imagine that you have a thin sheet of a metal like aluminum or gold and so forth. And here you're going to shine a beam of alpha particles, which are actually, later on we found out that this was helium-2 plus atom or ion. Okay, so now something interesting is that the mass of a helium-2 plus ion is about 7,000 times larger than the mass of an electron. Okay, so if we assume that this would be the size of one atom, and you have electrons somehow distributed like this, and then there's some positive charge to diffuse and randomly distributed in this atom inside that thin metal foil. Okay, what you should expect to have is that, well, if these nuclei are 7,000 heavier on electrons, okay, well, they should actually make it just right through and just have a straight trajectory. Okay, so you expect most particles to actually pass right through, helium to plus, and occasionally if you get very close to one electron, because this is positively charged and that is negatively charged, you might experience some deflections that should be very gentle. Okay, so maybe like that, or maybe like that. Okay, but that is actually something that was not observed at all. Instead, what was observed is that when you actually have that tin foil, or that aluminum or gold foil, a metal foil, okay, and you bombard these with alpha particles or helium-2 plus atoms. Okay, what happens here is that, sure, most of the particles make it through unchanged, okay, perhaps with little deflections, okay, but some of them actually bounce off in a backward way. They rebound very violently, and this was completely unexpected. Completely unexpected. Again, notice that the mass of these helium-2 ions is about 7,000 times greater than that of an electron. So something indicates that this model of the Plum pudding, okay, is actually not correct. Okay, it has to be something very, very heavy inside the atom, so that occasionally, when this alpha particle hits that part of the atom, okay, it actually is able to bounce back. Okay, so this kind of gave rise to the nuclear model of an atom. Right, so the idea here is that, well, an atom, if we take a cross-section of an atom, okay, an atom is going to have negatively charged electrons and so forth. But there's going to be a region of an atom where there's going to be positive charge, and that is going to be very, very concentrated. Okay, so let's assume that this is here at the center. Okay, so what happens is that if you now send these helium-2 plus alpha particles, right? Okay, so if they pass through right here, then they will not deflect. Nothing happens. The trajectory isn't changed. But if they actually send them in a trajectory where they collide with this heavily concentrated positive charge, okay, which has to be massive as well, okay, then at that particular point, then you should observe this deflection that was completely unexpected. Okay, so this disavowed the Plum pudding theory, where the positive charge was diffused, never concentrated in a particular region of space. Okay, and again gave credence to this idea that the positive charge and the mass of the atom should be concentrated in the center of the atom. Okay, and that again can explain these sharp deflections of alpha particles. Okay, so with these three experiments, the Thompson cathode-ray experiment, Millikan's determination of the mass of the electron, and the Rutherford deflection of alpha particles, we now have a really good understanding of what's going on in an atom. Okay, we have electrons that are negatively charged, pretty light, and then we have a positive region of the atom, okay, which is concentrated in a small region of space and is positively charged.